Section 7.4. Section 7.4, we're going to be adding, subtracting radical expressions. And we'll get right into examples. I just wanted to give you the rules, which are brief. So you can only add radicals if they are like terms. This is what's meant by simplifying. The question is, what makes a radical a like term? So a radical is a like term if they have the same index and if they have the same radicands. When we're talking about radicals, this number is called the index, and this number is called the radicand. The examples are fairly straightforward. The only time we might have a little hiccup in doing these problems is if we have to simplify the radical first. In our last lesson together, we talked about how to simplify radicals. I showed you two different ways. So I'm just going to ask you to simplify. If we had 7 root 2s minus 8 root 2s. The rule with radical is if the index and the radicands are the same, you just add the outsides. It's almost like doing 7x minus 8x. The answer would just be -1 root 2. That would be the answer. 7 root 2s minus 8 root 2s is -1 root 2s. You can put -1 in front, but you don't have to. All right. For our next example, what if we had 2 root 11 minus root 11 plus 3 times the square root of 44? Now this one's a little bit different because they don't all have the same radicand. But in our last class, we talked about how to simplify the square root of 44 two different ways. One thing we said we could do is we could say this is the square root of 44 is the same thing as 2 times 22, which is the same thing as 2 times 11. So when we go to simplify the square root of 44, it would just be 2 radical 11. That was one way we talked about doing this. The other way we talked about simplifying a radical is to find the largest perfect square that goes into it, which would be 4. Square root of 4 is just 2. You wind up with the same answer no matter how you do it. So going back to our problem, we have 2 square root of 11 minus the square root of 11 plus 3 times 2 square root of 11. 2 square root of 11 is what we simplified. So now let's just finish it up. 2 square root of 11 minus square root of 11 plus 6 root 11 is 2 minus 1 is 1. 1 plus 6 is 7 square root of 11. That would be the answer. What if we had 5 square root of 12y plus 6 square root of 75y? What we'd have to do is simplify first to get started. So the square root of 12y is the same thing as the square root of 12 times the square root of y. You can't simplify the square root of y, but the square root of 12 we could write as square root of 4 times the square root of 3, or 2 root 3 times root y. So the square root of 12y is just 2 square root of 3y. Looking to simplify the square root of 75y, well, the square root of 75y is the same thing as the square root of 75 times the square root of y. The square root of y you can't do anything with. 75, you could factor it down. You could do 5 times 15 and just keep factoring. But what's the biggest perfect square that goes into 75? 25. So simply we could just write the square root of 25 times the square root of 3 times the square root of 7. So simplifying the square root of 75 would just be 5 times the square root of 3 times the square root of y, or 6 times 5 root 3y. Some of these problems require a little bit of effort in order to get them to a place where you could simplify. So 10 square root of 3y plus 30 square root of 3y is 40 square root of 3y. What if we had 9 square root of 5 minus 4 square root of 10? So square root of 10 is just 2 times 5. That won't simplify. So these are not like terms. So you can't simplify. You can't force it to simplify either. You're not going to have a problem like this on your exam. All the problems are going to simplify, but sometimes, sometimes they can't. What if we had negative 2 times the 4th root of 32 minus 7 times the 4th root of 64p cubed? Sometimes what these problems amount to is even if you can't combine the individual terms, we just want to try to reduce those radicals. So with this, we're looking for a perfect 4th root of 32, or we're looking for a group of 4 of the same numbers. So the 4th root of 32 is the same thing as 2 times 16, which is 2 times 8, which is 2 times 4, or 2 times 2. We're looking for a group of 4. So there's a group of 4 right here. And there's a 2 left over. So simplified, this would just be negative 2 times 2 times the 4th root of 2. That's what the 4th root of 32 would simplify down to. Taking a look at the second one, we have the 4th root of 64pq. So the p and the q, we can't do anything with that. But 64 is the same thing as 2 times 32, which which is the same thing as 2 times 16, or 2 and 8, or 2 and 4, or 2 and 2. So you have a group of 2's. We're going to write this as 2 times the fourth root of what's left over. We have a 2 and a 2 left over, PQ. Or negative 4 times the fourth root of 2 minus 14 times the fourth root of 4 PQ. And that's it. That's all we could do with it. So we just had to simplify those two separate terms. What if we had the cubed root of p to the fourth, q to the seventh, minus the cubed root of 16 p squared q to the fifth? Let's break this down to mini problems. So this will be the cubed root of p to the fourth, which will take care of by itself. The cubed root of q to the seventh will take care of the cubed root of 16, cubed root of p to the second, and then the cubed root of q to the fifth. So we'll take care of all of these separately. If you remember, we talked about two different ways to simplify variables. One thing we talked about doing is if you have the nth root of x to the m, and you could simplify that to be a mixed fraction. We said that the answer would be x to the a times the c root of x to the b. I know sometimes the formula could be a little tricky, but if you take a look at the cubed root of p to the fourth, one thing that we could do for that is we could write this as p to the 4/3, which is the same thing as 1 and 1/3, or p to the first times the cubed root of p to the first. You could have also written p 4 times, circled the group, and then wrote 1 left over. You would have wound up with the same answer. Same thing with q to the 7th. If you want, you could write q 7 times, circle the groups of 3. How many groups of 3 would there be in 7? 2, with how many left over? So we would say q to the 2nd times the cubed root of q, like that. You guys just did that, right? You could also just write it 7 times. So clearly there's 2 groups. We wind up with the same answer. Minus group 16. This is just 2 and 8. 8 is 2 and 4. 4 is 2 and 2. So we have a group of 2's with 1 left over. We take out a group of 3 from p to the 2nd. No, so that's just fine the way it is. And then it looks like that last problem, there would be a group of 3 with 2 left over. Let's see if we could straighten this up and simplify it. We would just have When you're multiplying radicals, you multiply what's on the outside and you multiply what's on the inside. So this would just be p times q to the second times the cubed root of p cubed minus 2q times the cubed root of 2p squared q squared. It doesn't look like we have the same index. We also don't have the same radicand, so that's just fine separately the way that it's written. I want to finish with some fraction problems. What if we had 2 times the square root of 32 over 36 plus 2 times the square root of 27 over 108? The fastest way to do this is to reduce the fractions. So 32 over 36 is the same thing as 8/9. 27 over 108 reduces to just 1/4. And then we did talk about with radicals, when you have a radical for a fraction, you do it to the top and you do it to the bottom. I know the square root of 9 is 3. Square root of 1 is 1. Square root of 4 is 2. The only radical that we have that doesn't simplify is the square root of 8. But even still, I'll just do it off on the side. We could do a prime factorization tree, or we could just say this is the square root of 4 times the square root of 2. Or just 2 root 2. As far as what the answer would be, we could do 2 over 1 times this is 4 root 2 over 3 plus 2 times 1/2 is just 1. That would be a fine answer for me. You could also write, get a common denominator if you wanted, to write the 1 is 3 over 3 and say this is 4 root 2 plus 3 over 3. If you just got a common denominator. This is fine for me. Wanted to do a couple more of these. They look a little complicated to get started, but after a couple steps, they're just easy. What if we had 6 times the cubed root of 16 over x to the 12 plus 7 times the cubed root of 9 over x to the 9? We're going to do the same thing, right? So first thing we look to do is see if we could simplify 16 over x to the 12th. We can't do that, but we can do the cubed root of 16 over the cubed root of x to the 12th. Similarly, we could do the cubed root of 9 over the cubed root of x to the 9. We did talk about a property. When you have the nth root of x to the n power, we can convert that to a rational exponent. Nth root just turns into a fraction. Just be 6 times x to the 12 over 3, which is 4. Denominator with the 7 would be 9 over 3, which is 3. The cubed root of 16 would just be 2 and 8. 8 is 2 and 4. 4 is 2 and 2. So we have a group of 2s with 1 left over. The cubed root of 9, it doesn't look like we have any groupings here, so it's just 3 times 3. So we can't take anything out, that just stays the cubed root of 9. So 12 times the cubed root of 2 over x to the 4 plus 7 cubed root of 9 over x to the 3rd is what this would be totally simplified. So that would be a good enough answer for me. Sometimes you might have to get a common denominator. So the way we would just get a common denominator to add these fractions together is make both denominators x to the 4th. So you could also simply just multiply the top and bottom of this fraction by x, and you'd get 12 times the cubed root of 2 plus 7x cubed root of 9 all over x to the 4th. If you wanted to write it as a single fraction, that's how you would do it. There's one more problem that's very similar to this, and then we'll transition to our last section tonight. So if we had, let's say, 5 times the cubed root of 24 divided by y to the 9. Let me write it like this. Minus 4 times the cubed root of 7 over y to the 15. Just like before, we're going to take the cubed root of the numerator and the cubed root of the denominator. We'll simplify whatever we could simplify. So the cubed root of 24 is the same thing as 4 times 6. 2 times 2, 6 is 2 times 3. So it's like the cubed root of 24 would simplify to be 2 times the cubed root of 3. The cubed root of y to the 9th would just be y to the 3rd. Minus 4 times the cubed root of 7 won't simplify. Cubed root of y to the 15th is just y to the 5th. So we just get 10 times the cubed root of 3 over y to the 3rd minus 4 times the cubed root of 7 divided by y to the 5th. That's a good enough answer for me if you just leave this alone. But if you want to combine fractions, you could just multiply this left fraction by y squared over y squared, giving you 10 y to the 2nd times the cubed root of 3 minus 4 times the cubed root of 7 all over y to the 5th. So if you want, you could write it as one fraction just like that.